When an atom is placed in an electric field, we found that we could induce a dipole moment in it. And for an atom, it's pretty straightforward. What we had was a dipole moment was equal to the polarizability constant, which is alpha, times the electric field. However, for a molecule, it's a little bit more complicated. Now, the reason being is that for a molecule, the field may be at some angle to the axis. So what you must do then is you must resolve it into the parallel and the perpendicular components. So here we'll have our dipole moment will be equal to the parallel plus the perpendicular. And this induced dipole may not be in the same direction as the applied electric field. So essentially what you must do is obtain some linear relationship between the electric field and the dipole moment. And what this comes down to is the polarizability tensor. T-tensor. Okay, and we're going to have a dipole expression in the x, the y, and the z terms. So for x, what we'll have is a polarizability times x, e, and then we also have to write it in terms of for y and also for z. So you have a yx here plus yy plus z. And for z, it's the same thing again. Okay, so there we have it. That's a polarizability tensor. Now what we have is a set of 9 constants, which are given by alpha, I, j. And these 9 are located here. Okay, so these 9 constants will depend on the orientation of the axis which is chosen. And what you can do is you can choose the axis so that all of the alpha x, y, and x, z, and so forth are all 0, and we're just left with 3 non-zero components. And that would be the xx, yy, and the zz. Now, this linearization essentially tells us of a dielectrics response to an applied electric field.